Okay, time for the second lecture of the day. Okay, now here I want to talk about the remaining schedule, especially and of this semester. And one of the most important thing I think most of us, probably all of you, care about is the grading policy. Okay, we all want to now. So we will talk about the grading policy of this course now. Okay, now but here is my proposal. This is what is happening. This is the original schedule. Okay, now I published this schedule in the beginning, the first week of this course, right? Now we're supposed to have the second exam, midterm, today. But as we all know, due to the typhoon break, we delayed it, okay? But if we delayed it, let's say, if we have the second midterm exam, let's say next week, okay, we will have a problem because of the typhoon break. We miss 3 hours. So I don't have enough time to teach everything I'm supposed to teach, okay? And I don't want to delay the entire class by 1 week. But it doesn't mean that I don't want to put the extra work. That's something I'm supposed to do, right? But delayed it by 1 week, according to my previous experience, is not possible because people will come to me and say, come on, man, I'm busy. I need to go out for a vacation, okay? I already planned something else. I need to go out with my girlfriend, boyfriend, my family, or I'm not saying that in any negative sense. Everybody can plan their time, and I respect that. So delayed it by a week, I think is not an option, okay? Now, here, my proposal is, okay, let's just skip the second midterm, okay? Let's just have 2 exams, and your final semester grade is determined by the grade of these 2 exams, all right? Now, here is my grading policy, okay? If you disagree, we can talk. We can always talk and somehow come out with an arrangement that you think is fair. Let's say X1 represent the grade of my grade of the first exam, all right? Now, X2 represents my grade of the second exams. So we only have 2 exams. And the grading policy is we will have a Y. And the Y is 2/3 the maximum of X1 and X2 plus 1/3 the minimum of X1 and X2. Why do we do that? Because if we have more exams based on the principle of statistics, okay, it's like a sampling process. You have more samples. Your sampling result tends to be more reliable, okay? And I only have 2, if I have only 2 exams, what happened? I flunked one of the exams by accident, okay? By misfortune, okay? And it's not fair because one exam represents 50% of my grade, okay? So this, hopefully, this method, okay, will somehow compensate this uncertainty. All right, okay. Let's say this is the grade, okay? Now, we have many students. Let's say Y1 represent the semester grade of the first students, and Y2 represent the semester grade of the second students. All the way, let's say we have 51 students, all right? And I'll rearrange the order of these grades based on their magnitude, based on their values. Okay, let's say after this rearrangement, the highest score, the lowest grade is Z1, and the second lowest is Z2, and the highest grade is, let's say, Z51. Okay, now the median value is, of course, Z26. All right, whatever Z26 is, I will add a number. Let's say this number is M. So that is become, what is the grade of the A minus? 85? A minus is 80, all right? Okay. I'll add it up to 80, okay? Which means my intention is at least half of our students can have a grade of A minus. Remember, it can be higher because we have a policy of attendance. Okay? Okay? It means for 2 or fewer absences, the semester grade will automatically upgrade by 1 level. Okay? So let's say 80, no absence. Now your grade jumps from A minus to A according to this policy. Okay, we talk about this policy. You're supposed to know these policies, right? Okay. All right. So my intention is very clear. I don't want to flunk any people. But if, let's say, any students fail to participate in this learning process, he just don't show up, okay, then I think it's not fair. We give him a good grade, okay? But the reason why I want to give you good grades is because universities nowadays are inflating the grades. Yesterday, I read the news. 60% of the Harvard students get a grade higher than get a grade A or better, okay? So that was not the case 20 years ago, but people just doing that, okay? So I want to give you good grades to help you improve, to help your resume look better, okay? But the most important thing is still the learning itself, all right? Okay? So, do any people have any question or any issue with this policy? Okay, this policy means we don't have the second midterm. Okay, we will only have one midterm, which you already took, and then the final. So you have 2 grades. Okay, and you take the higher grade, whether it's the midterm or the final, it doesn't matter. Count it by 2/3, and you time 1/3 to the lower grade. Doesn't matter it's midterm or final, and this becomes your final original grade. Okay, original score or original grade, but we will adjust it to make sure that at least half of our students will have an A minus or better, okay? Now, if according to this formula, you are already A plus, okay, there is no way I can upgrade you 1 level higher, even you have a perfect attendance record, okay? So in that regard, please accept my sincere apologies, okay? But there is a reason for that, okay? But nevertheless, you still get A plus, and there is no better grade than A plus, all right? Okay, I hope you can. I'm not trying to please any people. That is not my intention. Pleasing students is the last thing I should do. Okay, the very thing I should do is to try to optimize the quality of this course. But I also know that grades matters a lot in your resume. Okay, and I also know that professors in other universities give grades unfairly. Okay, they inflated their grade. What is the easy thing for a professor to do? If I understand if I know I do a very poor job in teaching you, okay, and I know people are not very happy with this course, what do I do to make things right? Okay, to make things right, what I should do is somehow improve my teaching style. Okay, to make things easier to understand. Okay, to find out difficulties encountered by my students. But the quick and dirty solution for this problem is I simply get everybody good grades so I can shut you up. What are you complaining of? I already gave you an A. Don't complain. All right? Okay? That's one of the easiest things a professor can do. But please, 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 that is what I'm doing because I don't want to, I'm already too old. I don't need it because I'm a senior professor. In this stage of my career, I really have I really doesn't have any need to please to do this kind of placing job. Okay, all right. Okay, for peoples who don't speak Mandarin, please forgive me for a few seconds. Okay, because I have to clarify everything in Mandarin in case my English is not good enough. But I guarantee you what I said in Mandarin has already been spoken in English. OK， 这样子的策略可以吗？哦，有没有人有意见？了解吗？高分的乘2/3，低分的乘1/3，然后取出中位数调整，至少加到80分。好，所以至少一半的人是 A-。如果再有好的出席记录，成绩就在往上面再提一级。好，那我们就只有2次考试。好 ，OK， that's it. OK. Any disagreement? Any suggestion? Please. 好。每次考试的最高分还要加到9。No. 不会，就是 this formula applies to the final grade. Okay, not any independent grade. Not a grade of any independent exam. Okay, all right. 所以每一次考试不会独立计算，一定是用这个有利的公式算出来分数以后再去调整，好不好？So this formula applies to the result of 2 exams. Okay, all right. Okay. I forgot one formula. Okay. This is the formula. Okay, this is the formula we got. This is the scoring system that we are going to use. Okay, the scoring system. Okay, our scoring system is on this blackboard. Okay, all right. Let me ask again. Any suggestion? Any proposal? Any disagreement? Okay. Any people who is not happy with this policy? Any people who think this is unfavorable to me? I think it's not fair. I think it's not good. Tell me, you have to tell me now, okay? Because after that, everything's fixed. because people have to prepare what they need to do in the remaining part of this semester. Okay, if I change the policy all the time, it will create confusion and unnecessary inconveniences. All right, 这样可以吗？这样可以吗？ All right, so okay, this is it. This is the deal. All right, this is the final deal for our scoring system, for our grading policy. Everybody cool with it? Okay, thank you, thank you, thank you. I hate typhoon. Okay, I hate typhoon break. Okay, but I have to admit that the time I know that I was going to have a tough break. Actually, I'm feel relaxed. Wow, additional time for fun, for relaxation. But for the progress of this course, it creates, of course, inconveniences. Okay, but in any of the event, please let's do our best for the remaining part of this course. Okay. All right. Okay, that's it. All right. Okay, damn. Let's go back to short-term Fourier transform or short-time Fourier transform. Same thing. Okay. Now, what do we need to perform short-term Fourier transform? The purpose here is to analyze non-station signals. All right. Now, what are non-station signals? Non-station signals are signals whose frequency components vary with time. Okay. For example, this is a non-stationary signal. It's basically a sinusoidal signal whose frequency increases as time progresses. Okay. So its frequency component, of course, in this case, is a function of time. If you apply Fourier transform to determine the frequency components, you only get one amplitude and one phase spectrum. And that cannot be right because it does not have because a single representation of the spectrum cannot really tell us what is really going on inside this signal. All right, it's just not good enough. Okay, the tool is just not adequate. Okay, so this is why we need to use short-term Fourier transform to address this problem. The process including these three steps. The first, we divide the signal into short overlapping segments. Okay, like this. This is the first segment, and this is the second segment. It's like that we have a sliding window. By viewing behind the window and by moving the window as time progresses, we get a chance to understand how the frequency contents of that signals vary with time. Here we have one minor assumption. That is, within that window, within that small time frame, we assume the signal to be stationary. Okay? But actually it is not stationary. But if the time frame, if the time interval is small enough, then we assume that the frequency contents doesn't change much in that small time frame, in that small time interval. All right, that's the assumption here. Okay, after dividing the signal into short overlapping segments, then we apply Fourier transform to each segment. Okay, now to do that, we need to use a sliding window function. Okay, what is a sliding window function? We'll look at Hamming later. A sliding window function looks something like this. It means that we take the segment first, and then we tie the signal with this so-called window function. And the result is this, okay? So if you look at what we sample from the original signal, or what we took for the original signal, in terms of waveform, they are not exactly the same, right? Why? Because after segmentation, after windowing, we also multiply the segmented part of the signal with a predefined windowing function, such as this, all right? And then we take the Fourier transform, one segment at a time. And by viewing, I'm sorry, where does this come from? By viewing how this so-called energy spectrum vary with time, we have a good idea how the frequency contents of that signal changes with time, okay? Now, why is this important? Because in the real world, pretty much every signal is non-stationary. In the real world, pretty much every signal is non-stationary because the frequency components of every signal changes all the time. One simple example is our human voice, okay? As I speak, when I pronounce different words, its frequency components cannot be the same, okay? Now, after the application of the short-term Fourier transform, what is the output? We call the output spectrogram, which is a 2D representation of frequency versus time, all right? This is an example of spectrogram. Let's say this is the original signal, okay? To me, this looks like a human's voice, okay? Every burst of the signal probably correspond to one word, one Chinese word, okay? And here, what we have is, let's explain what a spectrogram is. Definition: a spectrogram is a visual representation of how a signal's frequency content changes over time, okay? Now, the x-axis, which is the horizontal axis, of course, represent time because we want to know how the frequency varies with time. Y-axis represent frequency, okay? Let's say from 500 hertz all the way up to, let's say, 7,000 hertz, okay? And the color, sometimes intensity. In this case, since we have a gray image, so it's the intensity. Intensity represents the power or magnitude at each time frequency plots. Okay, depends. You can choose power or you can choose empty magnitude. It's your call. Okay, so the darker the image means the higher the energy, for example. And so by viewing this spectrogram, okay, you can understand how the frequency components of that signal varies with time. And apparently from the spectrogram, it is very easy to understand this is a non-stationary signal because its frequency component are just not the same as time progresses, right? Okay, so this is very important and also very, very useful, okay? By viewing the spectrogram, pretty much you can understand the natures, the personality, the character, at least from a frequency domain perspective of that signal, okay? And the good thing is visualization. Visualizing. You don't look at numbers. You just check everything out by your own eyes. And you then have a very good idea what is really happening in terms of frequency, contents of the signal, all right? Now, short-term Fourier transform has one disadvantage, okay? That is time resolution versus frequency resolution, okay? That is, if I want to have good time resolution, I had to sacrifice frequency resolution, and vice versa, okay? We will explain why, okay? Now, to conduct short-term Fourier transforms, there are parameters that we need to specify, okay? The first is how large is the window, because it really matters, okay? The second thing is, which is probably not as important as window size, but it still really matters. That is the amount of overlap between windows. Do I want to overlap, let's say 30% of the window size, or 10% of the window size, or 20% of the size? It's your call, okay? Now, the key advantage of short-term Fourier transform is that it provides time localized frequency information. This is the key word, time localized. If something has happened, I want to pinpoint when does it happen, okay? When does it happen? That is what we call time localized operation. Now, there are also some limitations. The first is fixed resolution in time and frequency. We'll talk about that, okay? The second is it cannot achieve high resolution in both simultaneously, okay? If we want high resolution for the time, then more likely, then it's bound to be true. The frequency resolution will be compromised. Now, the first thing we need to do in applying short-term Fourier transform or short-time Fourier transform, or let's just call it STFT, is that we need to specify window size, okay? How do I specify window size? To do that, the first thing we need to do is how does the window size impacts the result of short-term Fourier transform? Okay, what will happen if I choose large window? What will happen if I reduce the size of the window? We need to know that before we make meaningful decision regarding to the choice of window size. Now, if I choose small window, which means I have high time resolution. What does that mean? A smaller time window captures changes in signal over short duration, giving better time resolution. Let me put it this way. If I choose my window size to be 0.5 seconds, that means I will examine the frequency contents of that signal, how they change it with time every 0.5 seconds. By contrast, if my window size is not 0.5 seconds, but it's 2 seconds, that pretty much tells us that I will check out what happened to the frequency contents of that signal every 2 seconds. Okay, not exactly every 2 seconds, but here let's just for the sake of simplicity, let's assume there is no overlapping. Okay, between windows. There is no overlapping. You can certainly do that. It's one of the possible choices in specifying overlapping. Nobody can tell you that overlapping is also always necessary, okay? Sometimes it is not, okay? You can do without it. But for the sake of simplicity, let's assume there's no overlapping. In that case, smaller window means you can check out the frequency contents. You can examine, you can inspect the frequency contents more frequently, which means you have better time resolution, okay? Okay, this is what we mean by time resolution, okay? It's pretty much, you can translate it to higher sampling rate, okay? But here, the sampling operation is not I want to sample the values of the signal. Here, the sampling operation means I want to take a sample of the frequency content of that signal so that I understand how the frequency content of that signals changes with time. However, a show window contains few data points, leading to poor frequency resolution. What does that mean? Remember the definition of exponential Fourier series, right? This is for exponential Fourier series for a periodic signal ft, okay? And we all know that the Dn is a spectrum, and it is actually a complex variable. And when we go to the complex plane of Dn, and if we view Dn by using a polar coordinate point of view, then the magnitude of Dn represents the amplitude spectrum, and the angle of Dn actually represents the phase spectrum. And amplitude spectrum are always even function of frequency, and phase spectrums is always an up function of frequency, right? And we talk about the value range of Dn, okay? We know that this is always true. It can be mathematically proven. So the value range of Dn is always this. That is, you have at the most N0 meaningful frequency components. You can only derive N0 meaningful frequency components by using what we call discrete Fourier transform. Now, what is N0? N0 is, of course, the number of sampling points. Okay, the number of sampling points. How many points that I can have in order to compute the spectrum. All right, how many sampling points that I have in computing frequency spectrum. Okay, if I have only N0 sampling points, then the meaningful Dn, of course, is at most this. All right, so let's go back to this sentence. A show window means few data points, which means N0 is smaller. When N0 is smaller, you have fewer number of D. You have fewer number of frequency components. So when you visualize the amplitude spectrum, you have fewer sampling points in the frequency domain, okay? Which means, let's say the original spectrum looks something like this. If you have 10 sampling points, which means it will probably distributed as this, 10 sampling points. If you have, let's say, 5 sampling points, then the distance between the neighboring frequencies of the sampling points in the frequency domains become larger. That is equal to poorer frequency resolution, okay? Now, so smaller window means I can increase the time resolution at the expense of poor frequency resolution. And things become exactly the opposite when we use large window, which means I have high frequency resolution because we have more data points in the time domain. Therefore, I will have more sampling points in the frequency domain. If I have more sampling points in the frequency domain, when I visualize the frequency contents of the spectrum of the signal that I'm dealing with, I have higher resolution. And that higher resolution means is what we call higher frequency resolution. However, the price that I need to pay is by doing that, I decrease the time resolution. Originally, I check out the frequency components, let's say every 0.5 seconds. Now, by using larger window, I inspect the frequency counter, let's say every 2 seconds. So which one has better time resolution? Of course, the one with smaller window, all right? Okay, now the other problem is what we are dealing with is not a signal, not the entire signal, okay? When applying short-term Fourier transform, remember, the first thing we do is we divide signal into a short overlapping segment, okay? The problem is by visualizing, by simply looking at the waveform that we took, that we segmented from the original signal, you know that they are not the same thing. What are the differences? First of all, and this is one of the most important part, this is only a subset of the original signal, not the entire signal. That is one problem. The other, by taking the Fourier the window function, okay, the waveform of the segmented signal, which is then later processed by Fourier transform, is not the same as the waveform of the original signal. Okay, now there is that one key question that we need to ask ourselves. Why do people use windowing function all the time? Okay, if I use windowing function, why can't I just use a rectangular function? If I take a rectangular function, then I multiply that power of signal by 1. So the shape of the signal remains the same. The only difference is I take a subset of the signal. I take a small part of that signal. But for that small part, it is remain identical to the appearance of the original signal. Okay? And that, at the first glance, should be a good choice because I have less distortion. By multiplying such a window, we create distortion, okay? But everybody do that. Why? Okay? The reason can be explained by the frequency contents of what we will get from the the result of short-term Fourier transform, okay? Now, remember, why do we use short-term Fourier transform or short-time Fourier transform in the first place? The key idea, the ultimate goal, is to determine the frequency components. That is the first goal. That pretty much the ultimate goal. Okay. So why not just use Fourier transform? Because the frequency, because we are dealing with non-stationary signal. So understanding the frequency contents of the signal is the first priority, all right? And what would happen if we apply Fourier transform to the original signal? Let's say this is the signal we are dealing with, okay? It is a very straightforward signal because it is nothing but a sinusoidal signal. It has only one frequency component in the frequency domain, which is a impulse function located at omega n minus omega, okay? The reason why we have this is a sinusoidal signal. It only has one frequency component, all right? The reason we have this is, we talked about this before. When it comes to amplitude spectrum is always an even function of frequency, all right? Now, let's say what we want to do is to perform short-term Fourier transform. So let's say this is our window function. I multiply this function with my original signal, and then let me take the Fourier transform. Okay, remember, what is the Fourier transform of rectangular signal? Sine C, all right? Sine C, all right? sine c, which is defined as sine x divided by x. Remember that? Okay. Now, let's see what happened. Now, once I take a segment of this signal, this is what I will get. Okay, this is the result of windowing, which is obtained by multiplying this with this. And remember, the original signal spectrum is this. But after taking a segment of the original signal, my spectrum becomes this. The resulting spectrum becomes this, which is different from this. This is the true spectrum. This is the spectrum of short-term Fourier transform. Okay, apparently there are some distortions. Okay, some information has been artificially created, which means some frequency components which was not there in the original frequency content of the signal, and they appear in the result of the short-term Fourier transform. How do I know this is the this is the spectrum of this signal? Very easy. We know frequency shifting property, right? Remember amplitude modulation. Think about this is a modulating signal, okay? And this is a spectrum. If I times a signal by a sinusoidal signal, what will happen? No matter what the original signal is, a spectrum will be shifted in the frequency domain. One half go to the right, the other half go to the left, okay? And the amount of shifting is proportional, not proportional. The amount of shifting is the frequency of the carrier signal, all right? Which is, in this case, omega z, all right? So let me emphasize, this is the true spectrum. And now this is the spectrum that we have after using short-term Fourier transform with rectangular function. Okay, so now we don't have the original spectrum. There are some distortions. All right, now this is the definition, the appearance. This is the definition of sine C function, and this is appearance. All right, now what we have, this is sine function. Now here, when we look at the structure of sine functions, we can divide it into two parts, the main lobe and the side lobe, okay? And the main lobe corresponds to the, when it comes to the distortion of the spectrum, the main lobes correspond to the phenomenon we call spreading, okay? Now, and the side lobes corresponding to a phenomenon we call leakage, okay? Now, the first thing we need to know is that we know this is a sine C function, and we know that the size of the spreading is inversely proportional to t, where t, according to this formula, is the size of the window. Okay, so in order to reduce the spreading, what I can do is I use a larger window. So if I use a larger window, that means this number of t becomes larger and the spreading becomes less severe. All right, so but the problem of bigger window is that the main drawback of using larger window to reduce spectrum leakage is that it reduces temporal resolution. Okay, we talk about this. Okay, check out the signal content every 0.5 seconds. is better than checking out the frequency components every 2 seconds. Okay. Now, we talk about time resolution. So if I enlarge the size of the window, it leads to poorer time resolution. And this makes it harder to pinpoint when exactly changes occurs in the signal. Okay. Sometimes this is exactly what we want. We want to pinpoint. We want to precisely localize when does a thing happen. Okay. Okay. All right. Now, after understanding the problem of spreading, let's talk about leakage. Now, when it comes to leakage, there is one fundamental need. Here, this envelope has an important property, has an important parameters, which is called the roll-off rate. It means the decay in speed of these side lobes. I know it is getting smaller and smaller as the frequency progresses, as the frequency increases, okay? But how fast it decays is characterized by the term we call roll-off rate. And apparently, I prefer large roll-off rate because these are leakage. These are frequency components which are not, which do not exist in the original signal. All right. So once they appear, I want them to go away as fast as possible. So what is the source of leakage? Where does it come from? Okay, if it is those frequency components, if they are not a part of the original signal, where do they come from? Okay, we need to figure that out. We need to figure that out. The leakage problem in the short-term Fourier transform arises when the final analysis window used in the transformation result in spectral components spreading into adjacent beams. And this is describing the phenomenon. Okay. Use a bigger window improves frequency resolution, reducing leakage, no problem. Why can larger window do that? The simple answer is, remember, after using a window, what we get from the signal is a subset of the original signal, a small portion of the signal, okay? Now, it's like a small symbol, okay? But if you want to guess what the original signal is, I think the intuition is clear. The larger the sample size is, the better result you will get, okay? Therefore, in the case of statistics, larger number of samples typically provide more reliable results than small number of samples, okay? That is why we plan to take 3 midterm exams, 3 exams instead of 2, okay? Because by doing that, hopefully we can more objectively evaluate how much you learn from this course, okay? But because of the time form, we have to compromise, okay? By using larger window, we increase the number of data points in computing the frequency contents via short-term Fourier transform, okay? So larger window, more information, of course, distortions such as spreading and leakage can be improved, okay? That is the root reason, the fundamental reason why increased window size is good for leakage and spreading, okay? What I mean good for is good for getting away or eliminating, or at least reduce the side effects of spreading a leakage. Okay, again, let's take a 10 minutes break.